I hope you had the time to relax around your lunch. Let us now resume with this last session of the World Power to X Summit. I said last, but not the least interesting one, because indeed, in this session, we will be having a deep dive into scientific and technology in the field of green hydrogen. We will be having distinguished scientific speakers in this session chaired by Professor Ahmed Angnawi. Professor Ahmed Angnawi is currently president of the Scientific Council of IRSN. He is deeply engaged for the establishment of mechanisms to support and reinforce R&D in the renewable energy. He served as head of the research group at Helmholtz of Material and Energy. He has deep expertise in processing materials and devices for solar energy conversion and thin chalcogenide solar cells. He is author and co-author of more than 200 peer-reviewed journal articles with H-index 44, numerous conference contributions. He edited 5 special issues and granted several patents. Professor Angnawi, the floor is yours.
Thank you so much. The organization of the summit. I will, before I start to share my presentation, I would like to say some words regarding the scientific part of this summit, and also to present the keynote speakers. However, I will first thank so much IRSN, the university, UP6, and all people behind the scene who work to make this summit successful, and it is indeed successful. So after my talk, it will be Professor Hannibal. He will talk. I will give more detail about his bio afterward. He's my colleague at Helmholtz Center Berlin since more than 20 years. At the time, Helmholtz was Hahn-Meitner Institute. Now it's Helmholtz Center Berlin. So I will give more afterward. Then it will come to Dr. Rashidi. He is one of the top scientists in IRSN, and he's in charge of bioenergy, hydrogen, and energy storage. So I will come back again to him. Then Professor Safiawi, he has a long-standing interest in Casablanca University on hydrogen technology, and he was involved in many projects, and I will also come back to him. And then Professor Hisham Ben Youssef, as far as I know, he is one of the most cited scientists in the university, Mohammed VI, and he's very specialized in fuel cell technology, and I will come back to him again. And then, last but not least, Dr. Leonard Stephen Sipai. I hope I pronounce your name well. And he's very expert and long-standing interest in methanol, from normal methanol and biology way to make methanol. And he has also cooperation with IRSN and University Mohammed VI, the new university. Do you see my slide here in order that I can start?
Yes, Professor, we are seeing it. You can go ahead.
Oh, okay. Thank you very much. So my presentation will be somehow general, in order it's an introduction to the whole session. And it is about Power to X, of course, and about research and development, and somehow learning from the nature. I had my habilitation in the Hannibal Institute long ago in 1983. I started, and I had the opportunity, and I was fortunate to work with one professor, Professor Helmut Tribuch. He's always inspired from the nature. That's why I have this culture of seeing the nature before making research. So I will talk about, I give an introduction about the towards CO2 neutral industry. I will talk about how the quantum solar energy conversion come to the questions, and I want to talk about the material energy solution before to go to the technology. And then I will just show one slide about how the research is running in Morocco and how it should be. So let's see here this scenario here. If you want to go to carbon neutral industry, and you know we have carbon dioxide, which is in all industry actually, which is responsible of climate change. That's one issue. We have electrical grid. In Morocco, we will inject by 2030 52% or 53%, as I heard, to the grid. Now, Ericsson have a huge initiative for water electrolysis and the production of hydrogen. Then we have to deal with the storage of this hydrogen. There are different ways of doing the storage. For example, one subject for the science and research in Morocco is the metal hydride, to store the hydrogen in materials. And this is one subject. Of course, there is the way to make electrolyzer in either by power supplying the electrolyzer from the solar energy, or also by using the artificial photosynthesis. And this is one of the talk where Professor Hannibal will give a very detailed and very exciting research he did by himself with Caltech, with Helmholtz, with Fraunhofer, and he's one of he has the top result and the record efficiency. He will talk about it. Science and technology is the important way to go toward carbon neutral. So one problem is the fuel cell, and we have our colleague from university, Mohammed Six. He will talk about it. You know that Morocco will go to a hydrogen vehicle in the future. And we have fuel cell with a lot of issue, like membrane, like catalysator. All are issue to be in the research portfolio in Morocco. Then we have the injection via pipeline, and this is, I hope one day we will see pipeline going from Morocco to Europe to Africa. And also I hope that we can find a solution that carbon oxide from the industry can be captured, utilized, and stored. And the possibility is the methanation. Methanation means that we have to do some research on catalysis, on material. Methane can be translated into other fuels. This is also another topic which will be, and also the Haber-Bosch process, which use hydrogen, which can come from green hydrogen and from nitrogen to form fertilizers, which is very important in Morocco and worldwide. Okay, well, what is the quantum solar energy conversion? As you know, photosynthesis has done a good job, and photosynthesis is a reduction process. This means someone has to give an electron and someone has to take the electron. Reduction is a gain of electron. Like oxidation is a loss of electron. So the plant take this electron from the sun, So it can gain energy from the sun. The energy is a photon energy. It will reduce hydrogen by some catalyst, natural catalyst, which we call coenzyme, and can take carbon dioxide out of the air. Then it will tax it to the carbohydrate like sugar, for example, and the plant can release oxygen into the atmosphere. Oxygen drives the metabolism of the most living organism on the earth. So all what we need is solar spectrum, which is already there, and we are blessed in Morocco to have a lot of sun, 100 watt per square meter, and every day. The question is how to go from to be inspired from the nature and to do this job. So we need to find systems which absorb the light, which effectively separate the charge, and which effectively transport the charge to have either electrical energy or fuel. Material energy solution prior the technology. We have to have a portfolio at the university and in our institute to control the material at the atomic and molecular level. We have to make combination of research and machine learning. And we have to screen material prior to the synthesis and testing in order to gain in the time and also money. The other problem what we have to think about is electrolyzer to respond sufficiently fast and to operate as demand response device with long duration. And one of the problem we have is to be able to detect the whole solar spectrum. We have small band gap materials which can give a small photovoltage, but it can give a high current. On the other side of the spectrum, we have large band gap material which can give small current but high voltage. And we have to find a way to use it. That is one topic of research and development. And Professor Hannibal will give you some examples which work very good. So what we get from a solar cell is the voltage and the current, and the product of these two elements will give us the power. That's why we need small band gap and high band gap to gain current and voltage, and to get this power output characteristic, which give you a what you see here. And this is, there are many issues where we have to do research in order to get it. So let's go back to this schematic here, where, as I told you, we have to have a band gap which is enough to absorb the whole light or big part of the light in order to have a high current. So we have a light absorption, charge separation. This means we have to have material which are rid of the recombination. This is also still research. There are a lot of research and development. The charge transport also there is a lot to do. And the electricity in the fuel cell is now the research what we want to do, which is already advanced in the industry, but there are many things to do in terms of upscaling. So the tandem solar cell is one of the promising elements for this kind of so research on tandem cell. There are now many ways to do tandem cell, and I expect from Professor Hannibal to give some details about it. So where we are now, we can generate electricity from the sun. We can produce hydrogen from the sun. We can make hydrogen using electrolyzer and PV, actually. there is photoelectrochemical process. All these issues will be discussed in our session 12. The production cost of the electrolyzer is still a problem, and it was discussed these 2 days, the first day and the day 2 of this summit. Photoelectrochemical cell take for water splitting, still in the lab scale, and has to go to the prototype and to the industry. This also will be good to discuss it today. I think a proof of concept from Thomas Hannibal, and it's not, we choose one of the best researcher on this topic. He's involved in a lot of projects, European projects, etc., and he will talk about this. So we have solar cells, we have electrolyzer, but we still have to go further to increase in terms of upscaling, in terms of the efficiency. We have to understand more which catalysis material we have to use for the production of hydrogen, as you see here in the schematic here. We can produce from water hydrogen, we can produce oxygen, but we need catalytic materials. So here is one schematic where we can see, for example, the photochemical solar cell. We can have the N-type material, which you see here, and we can have P-type material. We can combine both of them. And this is also one kind of direction in research what we have to work on. And you see here that you have a catalytic material which is driving kinetically the reaction. Even if a reaction is thermodynamically possible, you need a catalytic material in order to increase the kinetic and the rate of hydrogen production. You need to work on membrane in order that you have the right membrane to get the proton going to the other materials. And here also you need catalytic materials. So here you have material energy solution to work on. So there is thermodynamic, there is the kinetic, and you need a catalyst, you need even photocatalyst. The challenge we have, and the nature is able to resolve the problem, but not us, is the competing reaction to reduce carbon dioxide or produce hydrogen are very tight, as you see here. You have oxygen evolution and hydrogen evolution, and you need 1.23 volt at least to make this reaction. But there are many other reactions which can be involved here for the fixation or the capture of CO2, and how to be able to get rid of this competition reaction and to have only one reaction, or to be able to separate the process. And this is one of the topics what we have to work on it. So I show you here just a little bit more on this. You have the electronic and band structure of solid. And in Morocco, we have a lot of colleagues working on this in the theory, like density function theory, and they will talk about it at the end. You have semiconductor band gap. It's an issue. We have to work on material which give you the best semiconductor band gap. You have the position. If you have a semiconductor, you have to have the right composition in order that your valence band match this schematic here versus the hydrogen evolution. Sorry, here I have made 2 times hydrogen. One is hydrogen, one is oxygen. So it's a small mistake, but you understand what I say. Okay. I just want to show here one schematic from Thomas Hannibal, and he will give more about it. I'm very fascinated by the system where 3,5 compounds are in the position, are able to split water into oxygen and hydrogen. Hannibal will talk about it more. And there are a lot of progress done last just if I talk here, this picture from a National Renewable Energy Laboratory. From 2010 up to now, there are a lot of progress done, and in 3,5 compound, in perovskite, etc. All are topic what research and development has to be done. This is one system what I want to show you here, with where we combine the photoelectrochemical solar cell here in the left, and the PV or electrode, which is power supplied by PV from the other side. This kind of system, I choose it here in order to think about it, and maybe we can discuss it during during this discussion, where you can combine both the artificial photosynthesis and the hydrogen production using PV panels. That's one thing what I have choose. We can discuss it later. Another problem is the proton exchange membrane is also another subject where we have to work on it. We have to develop it. I think in Morocco we have to work on this very, very seriously, and exceptionally to try different catalysts. Actually, the catalysts for the anode, like this one, ruthenium, platinum, etc., are expensive. We have to think about oxide, etc. Platinum with carbon-based, it's also, we have to find an alternative. The same thing for the other electrode. And also, in my opinion, in all our institute, we should have a workshop where we can make small prototype, like the one here, where you can make your own bipolar plate and to try it before to go to the industry. So in Morocco, I witness and I work with many groups where we are very, very excellent in terms of theoretical calculation. And I know many groups in Morocco, they have a long-standing theory on ab initio, density function theory, molecular dynamic, Monte Carlo, etc. And actually, we are very, very good in Morocco in this. So fundamental research in terms of prediction is very good now. And actually, some colleagues start to think about machine learning in order to make the whole spectrum. And we will have a workshop, I think, next year about this with my colleague, Professor Benius from Rabat. And we are working on this workshop to make machine learning and to combine with all different theory. And so this part where to evaluate and simulate and the modeling is really an expertise in Morocco. Narrowing down the choose based on processing and economic, that's a topic where if we have enough possibility in Morocco, we can do it. We need to do experiment for that. We have theory, we have to do some screening, etc. Then identifying the suitable material for photovoltaic and storage. That's one issue where we have also to work on it. There are many groups that are working on this now, but we are not in the top, and we have to be in the top. Then come the next step, which is research and development. Identification of failure mechanism and proof of concept. That's where we have to be normally in order to communicate with the industry and to go to startup, etc. And this is also, we have to work on it and we can discuss it. Now, I want to say is that the IRISEN, since 2011, they have boosted this research. And actually, there are projects by IRISEN on technology readiness level 4, and they can give fund to do more research. This means in Morocco, the Minister of Education and Research has to give possibility to do research in this part here, what I show you in my laser, in order that we can be able to do the work for technology readiness level TR for and to go further. And this is actually, we are lucky that there are some universities, they have some possibility to go there and to present some project. But we can have better if we have more possibility. Then afterward, after the technology readiness level, we can go to the technology readiness 6, and the IRISN is giving found to push in this direction of prototyping and to go directly to the industry. That's the way we have to work, and I hope that during this discussion we can work in this direction. Now, at the end, I want first to thank you so much, to thank the organizers, because they have done wonderful work. All people behind the scene, they are doing very, very good work. And I want just to show this 4 item here. Hydrogen cost has to be competitive from production to the end use. Fuel cell electric vehicle can. And I remember when you take the group or the leadership. So I heard that my connection is not stable enough.
Oh, it's fine. I could hear you very well.
Okay.
I think, yeah, I already appreciate the very kind introduction and also your appreciation during your talk. Yeah, but I could hear you very well right now.
Okay, okay. So I just want to say that we know each other since 20 years, and I know when you have made all facilities on the not evaporation, but organometallic deposition of 3,5 compound in HZB. I forget your boss at the time, he passed away, but I forget his name. Then you have
Frank Willig, you mean?
Yeah, genau. Yes, that's it. Mm-hmm. And I remember how perfect you made a lab and very fast. And I hope that you can help us in Morocco in this area through collaboration, cooperation, etc. So now you are professor in Illinois University of Technology Institute of Physics. I know also that you are organizing a workshop every 2 years, every year. Quansol, I guess.
And this is also summer school, yes.
Yes, and I hope that one day you will bring this summer school to Ben Gurion. And that means some people, they come from outside of Morocco, from inside, and to have this synergy, I hope. So your research, you have this intelligence to make cooperation in Germany, in the United States, and everywhere, and you come with a world record efficiency in terms of 3,5 compound. You will maybe say something about it. And also, finally, you, in terms of solar cell emitting the nature artificial photosynthesis, we regret that our colleague and my friend Achim Leverens, he passed away. He was in Caltech, and I remember he invited me to come to Caltech to work with him, but I went to Qatar instead of Caltech, and I regretted a little bit, but anyway, that's another topic. So I will give you the floor. So please go ahead.
Yeah, thank you again and very much. And yeah, I'm very glad to contribute here always to the very impressive activities which I have followed in Morocco. This is really very good, and in really that sense which nowadays we need to go. And I hope this will go forward. And I would be very glad just to contribute. Yes, I think you already told many of the contents I'm working on and I'm dealing with my team here in Ilmenau in the group Fundamentals of Energy Materials. And in particular, I have fantastic co-workers, young scientists like Agnieszka Paszuk, who she's very perfect in epitaxial growth and in now photoelectrochemistry also. And we have new PhDs in a couple of projects. I will refer to this soon. And also in the past with great PhD students like Matthias May, who has now an ME Noether program. Then in addition, we have fantastic partners. This is important at such a complex challenge, which we are facing to. It's even more complex than converting solar energy to electricity, if we would like to convert it into solar fuels. And teams which we are strongly cooperating in the past and currently is the Joint Center of Artificial Photosynthesis, in particular Caltech, but also Berkeley Labs, with Harry Atwater at Caltech and Sophia Cheng and Matthias Richter. Also the Helmholtz Center Berlin for Materials and Energy, in particular Roel van der Kool. And this is also a fantastic and historical collaboration. The same is with Fraunhofer ISE, with Frank Dimroth. I'm working together already for more than 20 years. And team players in his team are David Lackner and Jens Ohlmann. And beyond this, we also have more collaborative partners. I'm just summarizing here in Tokyo University, Professor Masakazu Sugiyama and Alex Romaniuk in Czech Republic. We have a long ongoing interaction with Azure Space, who are fabricating high-performance solar cells, but also for terrestrial application. In a frame of a new project by the Federal Ministry of Research and Education in Germany, we have a very nice cooperation with TU München, Ian Sharp, who was before also at JCAP at Berkeley Labs. And just saying that we have a very good funding situation right now with DFG and BMBF and so on. So going into the contents, you explained it already well, Ahmed. The conversion of sunlight, of solar radiation, of heat radiation into chemical fuels, solar fuels. This is really a step which nature has shown us, which is very, very successful in nature, but hard to understand and hard to reproduce here on our planet artificially. So, and there's two ways. One is to just to provide free energy in form, for example, of electricity, and to convert this electric power into solar fuels. This is the two-step process. Different it is to do this directly, like an artificial leaf. This is the King's way, the direct way to convert sunlight like nature is doing. There is no wires, not different devices. There is just one artificial leaf, one photoelectrochemical device converting, like it is here nicely shown, solar radiation into solar fuels. And this can be done successfully with semiconductor devices, and this is a rather complex device. Attached on this are catalysts, and we have a surrounding by a solid liquid interface and the electrolyte. And finally, it is possible here at the cathodic reaction to produce hydrogen, and at the anodic reaction to produce oxygen. And this is the way we are trying to understand and to develop and to improve. And there is a couple of good reasons why this would be the King's way, the holy grail of photoelectrochemistry, to directly do this conversion. We have, of course, lower current densities if we do not concentrate solar light on a very high concentration. Even then, we have lower current densities than we have them at the solar radiation and electrolyzer combination. Then it is in principle thermodynamically more favorable to do this in this way, so we need less energy, total energy. Then, as I told, we have only one device which is independently scalable in all scales, like photovoltaics, small, middle, large systems. And we do not have additional electricity, no more circuit, it's just this one device. And we can, out of this, not only produce hydrogen, we can also produce fuels of higher complexity, like methane or methanol. And this is an issue which is even advanced, since there we need to have a high selectivity for the catalysts. And catalyst development is in general a big point here. At this solution with lower densities, this I did not explicitly say, we could also think about less precious catalysts than they are usually taken normally from ruthenium or rhodium or iridium or platinum. This is all very costly and precious catalysts, and in such a system here, it's possible to think about much less costly catalysts. Just to show you, I do not want to go in all details of this device. I just want to show you how complex it is. And this is even a reduced complexity, which I show you here. We have in the heart of everything a tandem cell. And I cannot show you this in educational slow motion, why we need a tandem. But it is possible to show this in 10 minutes, that you desperately need tandems to do this step, this conversion efficiently. So this is one very important point. Another very generic element is the interfaces. We already know this from many scientists, Nobel laureates, and so the interface is the device, and this holds even more true here. We have a lot of interfaces here, and one very critical one, which is the solid-liquid interface, semiconductor, catalysts, electrolyte, and gas development. So this is what you see here at the cathode. You see the tandem, you see the tunnel junction, you see the charge selective contacts, the catalysts themselves. The whole device suffers from low stability so far, and this is the most important point besides costs, which we need to work on. And here we have been successful recently in a very good cooperation. I already appreciated at the beginning of my talk with Caltech, which HZB, which Fraunhofer is, and this is what I want to show very quick here. One point besides others is in principle to have the appropriate semiconductors. They need to be very good semiconductors, and they need to have the appropriate band gaps, and that you can see here band gap combinations, different ones, and you see in the highest efficiency in the bull's eye we need a certain combination of 1 EV band gap for the bottom and around 1.7 EV for the high band gap, and then we are very successful and can get even well beyond 20% solar to hydrogen efficiency, which is really great. We realized this one here, this tandem, where there's some space for improvement, but however, it's already a very good value to show it is worth to work on this topic here. There's many points. I don't want to go into the detail here. I already mentioned, like the catalyst activity, which is very important, the stability, which is very important. I just want to spend some more few words on the costs, since this is, of course, for all of us, the strongest parameter, since we need to drive this with our economy. And I also don't want to go into the detail of this slide. This is just a slide to motivate again that we have a high breakthrough technology. If we would combine the high performance semiconductors, 3-5 semiconductors, with the working horse of semiconductors, the silicon. So there's advantages which should be combined, and there is some success also recently to combine them. We are already working for a long time to understand this very difficult combination here. And together with Fraunhofer ISE has impressive results recently. This is also an older one nowadays. We have a new record here with an efficiency of almost 26%, which is already very good for the combination of C5 and silicon. This is really a major point, and where we have now a very nice new project working together to do a demonstrator with this 3-5 on silicon for hydrogen production. Just some more words here to show you. Of course, the costs nowadays for such a device, which we have realized is too high, of course. But we have seen in the success story of PV that it is possible to get the costs down by orders of magnitude by working on, and this is here just a picture, how costs could get down from this precious record device structures towards low-cost device structures by combining them firstly with silicon, then looking to all the parameters of the growth process of the silicon substrates, on the handling of all the materials involving waste management and the back end of line. So there is a lot of screws which we can drive and which could bring the costs down. Even low concentration could be one more parameter to do this, to get really competitive, cost-competitive costs for such devices. This I also jump over. It just should tell you that there is many different ideas how to use this. This is really future technology which is worth to work on, since this is different breakthrough technologies combined in one complex device. And just last but not least, I would like to show what should we do and how is the conclusion. We see it's a disruptive method to produce clean fuels. We need still research to support this, to bring this into the field. But there is already very good, how to say, very good starts to do this with demonstrator development, which we are actually working on. It's really the next generation technology, and it combines different expertise from different fields with different generic elements of research and development. This is the stability, the light harvesting elements, the optoelectronics behind this, the prototype, the demonstrator development, and of course, in total, we need to go into new fields of advanced characterization, like at solid liquid interfaces, for example, with synchrotron radiation. And so last but not least, I would like to thank you for inviting me here and for listening to and looking at this talk. Thank you.
So thank you for this overview, Professor Hannibal. I will now go to our gentleman, Professor Rashid. He's expert in thermal system and Power-to-X at Ericsson. And since 2018, but before he worked on in Mazen and also in France. And actually his focus is bioenergy, hydrogen, energy storage. And I think as far as I believe, I know, he is the driving force for this Power-to-X in Ericsson, in Belgrade. And I give him the floor and I wish him a lot of success.
Thank you very much, Professor Angnawi. It's really an honor that you give me by this kind introduction. It's really a teamwork here in Morocco, and we are really happy to see that Morocco now is put on the radar not only as a future exporter of green molecules, but also a contributor and a strong partner for developing pilot and industrial projects together with our partners in Europe and beyond. So my talk will be less technical, less scientifically, let's say, prestigious, but the idea is to present to the participants the vision that we have through the implementation of an R&D platform dedicated to Power-to-X and green hydrogen and applications called Green H2A. So we would like this platform to be a sort of technological back office and an R&D hub for the Power-to-X ecosystem, both in Morocco and also together in partnership with our countries, other countries that will collaborate on this subject. So without further ado, I will start my slide. I hope everything is okay, technically speaking. I see that my screen is shared, so yeah, so this platform is part of a network, a national network of R&D platforms that are already being initiated by Ericsson under the umbrella of the ministry, but also with the strong support of our strategic partner OCP and University Mohammed VI Polytechnic and its ecosystem. And now we are the third platform being under preparation to be launched next year, inshallah, as we say here in Morocco, if everything is all right. After two successful launches of two platforms in Belgrade as well. The first one, the Green Energy Park, inaugurated in early 2017, but also the Green and Smart Building Park that has been finalized this year and is already operational. As all the platforms, since our, let's say, goal is to bridge the gap between the early stage R&D in university and also the industry and the market, or the industrial ecosystem, the idea is also to benefit from the, as you said, Professor Angnawi, from the Moroccan expertise locally in material science, in material modeling, etc. Both from Moroccan eminent scientists in Morocco, but also in the diaspora like yourself and other many brilliant minds that would like also to gather around this project. And the idea also by involving industrials such as OCP and others like private people from the private sector, we can scale up successfully the first, let's say, industrial references projects in Morocco. So this is a vision on how we see this platform, a mixture between indoor labs and outdoor open sky labs, if I may express myself this way, in order to test, to qualify, but also to try to understand and help scale up technologies on complementary sizes, probably to go up to the megawatt scale in the outdoor demo or pilot units. And our focus here is really, for the short term, is really to understand the whole main, let's say, technology bricks being involved into the green hydrogen and its application, Power-to-X value chain. So we are focused on the upstream by understanding and trying to figure out what would be the better mixture or hybridization between renewable power in order to qualify or to have the more capacity factor for the energizing, let's say, the next critical path component, which is the electrolyzers. So we need to exploit them at optimal, let's say, conditions. But also we are focusing as well on the downstream in terms of applications, especially for Morocco, two main applications, the ammonia synthesis, since we are a big actor in the phosphate economy, but also methanol and other e-fuels or e-molecules or green molecules in order to orient them to the export. And ammonia, by the way, is also a nice vector to export hydrogen to the offtake markets. So the idea, as I said, is really to take the trend as quickly as possible and not to double the R&D that is already being done by other prestigious, let's say, centers, but to be, let's say, complementary, and also to train and to have expertise locally to be able to engage very quickly into very important projects together with international, let's say, partners. And then in the second time, the objective is to decide on what would be our R&D roadmap, given the priorities of Morocco, but also with the, let's say, the partners that will be for sure involved in the governance of this green hydrogen and application platform, Green H2A. So really, very quickly, a presentation of a portfolio that we have developed since like 2 years now, a little bit more, but some portfolio that we have already started, besides the work we have been doing in terms of studies and PowerPoint, etc. So we are also preparing not only the PowerPoint, but also the power plants. So it's my pleasure now to present you some briefs on key projects that we are working on. The first one is a sort of an in-house project that is funded by IRSN, which aims towards the setup of a Power-to-X micropilot unit. So we have already acquired the electrolyzers that is now being installed in Ben Guerir, but also we are working on the whole chain value. The idea is really to have a small tool for research and training. So we have a capacity around 20 kilowatt electric, but we would like also we are already working, on the upstream. So we have modeled a little bit some optimization of hybridization. We have some in-house models for the electrolyzer parts, but also we have already started simulation of production of green ammonia and green methanol here under a variable electricity. Second project is that will be launched hopefully in the quarter of next year, quarter one of next year, is the hydrogen storage in the salt caverns. This is really, for the specialists that already know, this is a key issue. Storage of hydrogen going from those spheres and those cylinders is really key, because it can cost a lot, because those storage units are based on steel and it's expensive. But if we can use some already existing salt caverns that are quite free, but also huge in terms of capacity. So this gives us really a very competitive way of storing and handling hydrogen for exports or for domestic use. So this is also a project together with SOMAS, which have already 3 salt caverns in Mohammedia, in the region of Mohammedia. I think they are already exploiting one of them, and we are engaged together with the University of Notofail, HDF in France, and Enagaz in Spain into research projects to start a sort of feasibility study of using those salt caverns for storage here in Morocco. Second, let's say, key project, this was one of the first projects that we have promoted together with our colleagues and partners from OCP, which is the green ammonia pilot project of a capacity around 4 megawatts electric and around 4 tons per day. And the idea, together with our partners from Green Energy Park, Fraunhofer, University of Mohammed VI Polytechnique, and JESA, the idea is really to assess the technology and not to wait for big projects to come, but really to have hands-on. This is really a strategic view from OCP, and also always in mind to have this scale-up opportunities that may arise very quickly, depending, of course, on the cost, as Professor Hannibal have recalled. And this is a project being supported by the BMZ, so the cooperation, the Federal Ministry of Cooperation and of Economic Cooperation in Germany, but via also the KfW. Third project now ongoing is what we call Ptx Pathways, and this is a project of power to liquid. So the idea is to have a pilot unit here in Morocco to produce liquids that comes from hydrogen, green hydrogen, but also combined with CO2 extracted either from the air, direct air extraction, or from an existing chemical plant like a cemetery or any other plant producing carbon. And the idea is also to assess technologies, to see also the perspectives, but also to assess the feasibility of the markets, and especially into both for the domestic and also for the export. And this is a project that is being supported by the BMU, the Federal Ministry, Federal German Ministry of Environment. Last projects that I will give you a brief on is Menolink Project. This is also just at the beginning of the scoping mission of the projects. We have also a partnership with the Navigant Islamic Bank of Development, Alcor, AG, Edis Rekre, and Fraunhofer, Easy, Renak, Shura in Turkey, and also Jordan. So this is the idea is really to link ambitious renewable energy development and efficient sector coupling in the MENA region. So we have contributors or partners from Morocco, Tunisia, Egypt, Saudi Arabia, Jordan, Turkey, and Germany. So quite a good consortium, and the idea is really to have a holistic view both from the technology demonstration part, but also policy, funding, and also the capacity building, etc. Last point of my presentation is I want also to give you some preliminary results that we are having concerning some technical economic assessments we have already done with my colleagues here in Morocco about implementation of projects on Power2X. So this is what I told you. The idea was really to tackle the whole value chain from the upstream and the mixing of renewables until the simulation or the chemical applications. And here you have some slides that are extracted from an ongoing work about the comparison between two sites. And here let's say, to give you some idea, the size is around 5 megawatt scale. Of electrolysis, and the capital, let's say, expenses is around 15 million euros. So we have the same capex, and for two different sites we can achieve. We see here that for just by changing the size for the same capex exactly and the same size, we can have interesting prices for the kilogram of hydrogen, or costs of kilogram of hydrogen between two sites, and also depending on the configuration that we give in terms of the unmet hydrogen load. So, also an interesting point is to see the contrast between the two sides. The side of the north is mainly composing his hybridization from renewable energy by wind, whereas the southern sides, the majority, one third to 2/3, is through the photovoltaic. So this is quite interesting, and we are continuing the study now for a 100 megawatt scale plant. Another aspect which is really also interesting is the factor or the electrolyzer's load, depending on the day of the year, etc. So here we have a comparison between the two sites, the sites to the north and the sites to the south, in terms of capacity factor for the electrolyzers or the load factor of the electrolyzers. And here it can be also interesting when we would like to choose between technologies, because we know that there is alkaline, PEM, and high temperature technologies. Here we can see that, for example, for some technologies that but that are not really designed to low load factors, that cannot be probably useful or relevant for some cases when we have very low load factors. Here also a very interesting aspect on the sizing of the buffer of the hydrogen storage that I have started to speak with, because this is really key. Because as you know, everyone, industrial processes or chemical processes that we would like to make green are generally 24/7 processes, so they don't need to stop in order to be competitive and also to maximize the OPEX. So the idea here with the renewables, since the electricity will be variable, is also to really conceive and have a very good design of the buffer of the storage of hydrogen. We cannot downsize it, because then we will have interruptions in the chemical plant, but we cannot neither oversize it, because we will have a very big capex. So the idea is to find really a compromise, a win-win situation where we can have an estimation of what would be the optimal size of storage. Here you can see, for example, that optimum size can be around 600 cubic meters for hydrogen for this around 5 megawatt plant, which is really interesting. And also you can see if we would like to have very continuous production without having a buffer, then the storage can be up to 2,000, let's say, cubic meters. So this is really a key element that we've got here, and I wanted to share this with you. As I told you, work is really continuing with my colleagues to go to further scales. So with this, I would like to thank you very much for your time and being so kind to listen to me. And I would like, most and foremost, thank my colleagues in the team, Nohaila, Ayoub, Ilham, and Osama, but also other colleagues, Abdul Taif and Fatem Zahra, and all the PhD and students, master students that helped elaborate this work. Thank you very much to all of you.
So thank you, Rashid, for this overview of the new facilities and new work from IRISM. Obviously, IRISM have made a huge progress, and I see that this is our graduate students in Morocco are fortunate to have IRISM, where they can make their training for their master degree, PhD, and work there. That's from one side, and we know already that there are many students that come to the Ben Guerir. It's a hub now, and actually I see that you have done a lot of progress, and also I witnessed that you have a big cooperation with Europe, with Germany, Fraunhofer, and so on. And this is a very important example for other institutions. So I will come back to you to discuss in detail many issues, but I want to go to Professor Dinoun Safiawi from Casablanca. Do you hear me? So Professor Dinoun is a professor at Hassan II University in Casablanca. He is an expert in renewable energy, plasma physics fusion, desalination of brackish and seawater. At present, Professor Safiawi is director of the Renewable Energy and Dynamic System Laboratory at Hassan II University. He is coordinator of multi-source system combined renewable energy and hydrogen project in order to supreme intermittency energy system. I want to thank Professor Dinoun. I know him since many years, and he's working very hard, and the floor is yours. Professor Dinoun?
Assalamu alaikum. Ahmed?
Go ahead.
You see my presentation?
Yes, sure.
Sure, good. Assalamu alaikum Bada. I am very happy to participate in Ptx like a speaker on one hydrogen technology for mobile systems and innovation. First, we want thanks to collaborators and partners. My thanks go to Mr. Badr Iken Samir Rashidi for discussion, collaboration, and invitation as speaker in Ptx Summit. In second, as well as to Vice President of OCP Khribga, Mr. Alwani, and Mr. Swelhi, Director of General Simadi in Jorfsfar, for their support and collaboration. Also, my thanks also go to my colleagues in our laboratory and industrial company. Summary of my presentation. First, we discussed multi-source system based on renewable energies and hydrogen. In first part, we discussed hybrid, car, battery, and fuel cell. In the second, hybrid scooter, battery, and fuel cell. In three parts, methanol, ethanol, or ammonia for gasoline engine. In four parts, hybrid car, fuel cell, and ammonia. In final, 5 automobile desalination plant in the Grain Park, supplied by multi-source system on renewable energies and hydrogen. In our laboratory, we are developing within framework of the project funded by Hassan II University on multi-sources systems based renewable energies and hydrogen to supply desalination plant. Multi-source is composed by by 14 kilowatt peak and 18,000 18,000 ampere hour producing the three phases in order to alimент one unit of desalination. Also, our system.
Excuse me, can you make full screen? Downstairs, and then you just make full screen.
Good.
Yes. Yes, good.
That is the storage from solar energy, the battery with 18 ampere hour producing the three phases in order to alimент the unit of desalination. That is the principal element of our systems, multi-sources. That is the principal element in our multi-source systems. We add 1 kilowatt fuel cell in order to reduce the intermittence of renewable energies. That is the system unit desalination alimented by our multi-source systems added with fuel cell in order to desalinate the brackish water for producing the potable water. In the second part, we have studied the car hydrogen and electrical car hybrids by hydrogen. Here we have one car, hydrogen car, that is completely alimented by fuel cell. In the picture we have the system. We have one electric motor alimented by fuel cell with hydrogen tank. Also, alors, in emission is very good. In emission, we have column, water, and head. In the second situation, here we have a car hybridized by electrical car hybridized by hydrogen. In the diagram, we have hydrogen tank, fuel cell stack, battery, control motor, et electric motor. In three parts, we have also experimented the hybridization of the scooter battery with the fuel cell to increase the autonomy scooter. On the road, the autonomy depends on the reserve of hydrogen. Like cars, the autonomy of cars, for example, here, one car's here, the autonomy crisis. In order, if I have the reserve of hydrogen, you can crisis the autonomy. Here we show the picture diagram of one scooter hybridized by hydrogen. Donc you have hydrogen tank, you have battery, you have fuel cell. Fuel cell give current for motor. In three parts, we have studied the fuel mixing of a thermal engine. In this study, we have mixed transformation that represent how with the gas and gasoline. Now we are working on hybridization of the gas and, excuse me, In this study, we study hybridization, for example, gasoline with methanol, or gasoline with ethanol, with the right of mixing is alors here, the right in mixing. Moment, please. We mix alors the gasoline with the ethanol or methanol with one calculated of dividend of mass of gasoline and methanol, 15% for gasoline and 85% for methanol. The gasoline accelerates the combustion of ethanol. Here we have in this picture one car consuming the ethanol or methanol. In the right, we have process producing the methanol or ethanol. Also, in our laboratory, you have a motor of gasoline. With this motor, we experiment mixing ethanol with diesel with a percentage 15% for gasoline and 85% for ethanol. Also, we go to another experiment mixing ammonia with diesel. Also, experiment the motor for alimented motor with the heat produced by cracking of ammonia. Our aim in the experiment is to encourage farmers to make and use ethanol and methanol as fuel for their agriculture machinery on their farms. In the fourth part, we study the hybridization of car battery with the fuel cell in order to increase the autonomy of car on the road if you have a reserve of hydrogen bottles. Here we have a car. Here we present the study of hybridization of the fuel cell and the heat engine that consume ammonia, heat produced by the cracking ammonia. In the process, you have electrolysis, for example, producing hydrogen alimented by renewable energy like solar energy and wind energy. Producing hydrogen for fuel cell giving electricity for electrical motor. Other motor can be function with the heat producing from cracking ammonia, producing in one reactor synthesis of ammonia. As part of this innovation, we have deposed one patent, the heat engine that works with two possibilities, mixture of 15% diesel and 84% ammoniac, or thermal engine that works some percent with the heat coming from cracking ammonia. With my parts in OCP, Mr. Alwani and Mr. Swalhi, the OCP developed a prototype in order to synthesize ammonia for many applications. First application, fertilizers, engine, UCP information, UCP import 2 million tons of ammoniac. Our objective is reduce importation of ammonia by OCP in Morocco with this development of this reaction. And final, we have one program I discussed with Professor Badr. In the future, we develop one installation of desalination of brackish water in the hydric basin, Bhera, Hamna. What basin is Green Park, Belgrade, in collaboration with OCP, IMCSP Foundation, OCP Erizane, EH2, Faculty of Sciences Casablanca. This operation is composed, this process is composed by 20 kilo solar energy, 10 kilo wind energy, alimented the electrodes with power 20 kilo. After the electrodes producing the energy for fuel cell alimented one unit for desalination in order to produce 15 meters squared by hour. We have patent deposits in OMPIC for conception system. Here we show the process of desalination of brackish water. The process is composed by forage, after pumping, after operation.
We still have 2 minutes.
Huh?
2 minutes.
Oh, good. After we go to filtration, vertical filtration. After we have nanofiltration. After we have osmosis inverse giving water with 0.5 gram by liter. That is very good result for desalination. This operation can help many people in Hamna or in Morocco in order to have two possibilities of potable water or irrigation water. Thank you very much.
Thank you very much for this overview on your activities, research, and education also, and in good harmony with the community and what's the need in Morocco. And this is an example of a professor at the university who did his good job. Thank you very much. So I will go to my colleague, Professor Hisham Ben Youssef. He is Associate Professor at High Throughput Multidisciplinary Research Laboratory at Mohammed VI Polytechnic University. As you know, University Mohammed VI is a new university in Benguir, close to Erizan, and with a high collaboration with Erizan as well. Hisham Ben Youssef, he developed a wide expertise on physicochemical analysis technique and electrochemical technique as well, and polymer and composite material processing. So his field of entry is fuel solar cell and related subject. His research actually focused on the development of a new smart material for different applications, such as membrane technology, sensor, coating, electrochemical energy storage and conversion, fuel cell batteries toward competitive target. Thank you, Professor Hisham, for coming, and we are looking forward to hear your activities, and the floor is yours.
Thank you, Professor Angnawi. Thank you, Mr. Chairman, for this nice introduction. I had the pleasure to meet you once in person in Rabat 2 years ago, and since then we didn't meet. But I hope that it will be not the last time to meet you in Benguir next time you are here. Then thank you also, dear colleagues, audience. My presentation will be, let's say, related to technology, fuel cells as a key technology, hydrogen ecosystem, and emerging economy. I think there were a lot of discussions about the Ptx, and then I think fuel cell is a key. Is a key in that sense to link some parts. I would like to start first with some facts, which are, I think, well known and expressed every time. Let's say the transport counts for a quarter of the CO2 emissions. We have a lot of air pollutions, and now there are discussions always about the health and the impact on and also the connection with the premature deaths in Europe or in some countries, which is quite rather scary when you see the numbers. Also, there are, as I mentioned, and I was facing that, a lot of cities, especially in Europe, also in recent years, they are forced to shut down their roads, traffic, due to the concentration of pollutants. And this also is a fact, a matter of really increase of this or damage of the let's say, of these pollutants related to the transportations. Of course, everybody agrees that there is an urgent actions plan which must roll up to develop clean renewable energies and zero emission transportation. I think when you see all the scenarios which are already, let's say, broad and strategies, all, let's say, converge to the fact that also hydrogen will be a key player toward this decarbonization, which everybody talks about. And matter of fact, when I'm looking now to I was taking yesterday to check the members of the Hydrogen Council. You can see that that consensus is quite clear that also hydrogen and green hydrogen especially will be definitely part of the future scenarios, and also will be part of sustainable energy ecosystem. And it's interesting also for me when I see also some names here to check the members. You can see that even petrochemical world leaders like Aramco in Saudi Arabia, Sinopec in China, and Shell also are part in it, let's say, and they are partners in this council with the other automotive companies like Toyota and others also in Korea. I like to let's say to express some key properties. People are also talking about really regulations, safety, and so on related to hydrogen, which is quite will be also a part of the discussions in the coming, let's say, years in Morocco. If we are going to this kind of technology, new technology, the fact is that hydrogen also is having some physical properties which are to be taken seriously. Even they are well controlled since, how to say, years and years. The physical properties related to the difficulty to contain it, because it's really the smallest of all molecules, let's say. Also, it has extremely low density at normal, let's say, temperature and pressure. Of course, the chemical properties related to the high flammability, as I mentioned, this explosivity or the explosive mixture with air from 4% to 75%. And of course, we don't, let's say, forget the ignition energy also, which is extremely low. Also, matter of fact, it has also some let's say, other compatibilities issues, but especially with some alloys and which are quite known for titanium, nickel, and other stuff. Just looking back, let's say, to the history, I liked always to mention this, let's say, years where the story began with Johann Wilhelm Ritter in 1800, and then afterwards the Christian Friedrich Schönbein for the discovery of fuel cells in 1838. But it is not possible to forget also the Jules Verne, let's say, and the famous, let's say, statement, "Water is the coal of the future." And I think it's quite premonitory to see this kind of statements in this century. Of course, the fuel cells as an efficient conversion technology, and as a clean energy carrier to reduce CO2 emissions, will contribute for sure to this ecosystem, which is now starting to be built. As you can see, we have a lot of, in my opinion, a lot of applications which were already demonstrated and prototypes validated in a large extent. Let's say, how do you say, military, stationary, and others, really, even for this fuel cell powered minibar for trains operators and so on. But it's difficult was difficult or still difficult to level up the market in a consistent way and a sustainable way. I see also a lot of directions toward also going towards, let's say, the use of beyond or going beyond the traditional, let's say, use of hydrogen with some opportunities, and especially the ones in Germany. I see some rail or train already operating, and which was having a clearance, which is quite a good, let's say, point in the legislative or the policy for the policymakers. And also other projects are appearing in that sense for maritime and so on. I think if I go more into the let's say the transportation issue, let's say sector, we have really there is a lot of worldwide attraction to this technology, but especially I made here selection of some tracks which are now commercialized, and recently I think Hyundai was really shipping a lot of these tracks in Europe and in some countries. And it's quite nicely seen that we are, let's say, hitting this part, even though the cost and availability of hydrogen and also other factors related to the policies, it's really, and regulations has to be still addressed and to be well shaped. In reality, fuel cells are always hybridized, and maybe my colleagues, also the professor before me, he was also commenting some mixture or mix of things, batteries and so on. And it's in reality, it's related also to this, let's say, the hybridization of this electrochemical device is related also to their, let's say, specifications. And as I mentioned here in this Ragon plot, that when you have a fuel cell, you might, let's say, drive for a long and continuous load, let's say. And of course, while you are stopping, you can charge your battery, and think of it also when you want to restart. I think supercapacitor is a good starter, and you can really get a punch to start and be in action. And of course, here I mentioned some comparison between these three technologies, and of course, still for fuel cell, the high cost it's quite big. Now, if I go into detail now to the heart of this proton exchange membrane fuel cell, which is used in automotive applications, Of course, it's conducting electrolyte. It allows for charge separation, but as you can see it here, the half cell reaction take place at the catalytic sites of the electrodes, and we have one side, let's say the hydrogen oxidation occurs, and then we have in the cathode side we have the oxygen reduction reaction, and of course the setup is quite shown here. You have always a membrane, you have electrodes, supported catalysts, and then afterwards you have also the bipolar plates, which are normally making the MEA cell or single cell, let's say. Now, if we go to let's say more detail, we have to have in mind that when, for example, car makers, they are discussing let's say a specification on more related basics to the stack scale. And of course, when we want to study, really understand also all the phenomena of degradations, also chemical degradations, mechanical degradations, for example, catalyst dissolutions, or even pinhole formations in the membranes, we need to have a deep diving on the microstructural or the micro scale, and of course linking it afterwards also to the cell scale. Now if we look now into deep to the different phenomena, we have of course a lot of phenomena of transport of reactants, complicated, let's say, complex processes related to different diffusive and convection phenomena. But of course, the most important part is really the separation phase, of course, of these two phases between the flow of the gases and also the flow back of the liquid in that sense. I will not go into details to explain all this. That I want just to go to the, let's say, to the part related to, as I mentioned, the heart of the system. Also, it was mentioned by Professor Angnawi, is the proton exchange membrane, and it has to fulfill, let's say, two main, let's say, functionalities: transport the protons and also separate two compartments, because we are talking about electrochemical device which has two sides, let's say, anode and cathode, or positive and negative. Of course, it has to be chemically stable against oxidative let's say, species, thermally stable and mechanically stable. Now, just for when we go to let's say, discuss about this, one of the main challenges, as mentioned, also is the stability or this polymer electrolyte or this proton exchange membrane. And one of the idea really to focus in really on developing tools to follow up in situ this degradation, to see what is happening there. And until now, I think there is no clear message on how these synergies between chemicals, mechanicals, and thermal degradation is occurring, and what are the synergies between these phenomena. But the fact is that, as you can see it here, after 2000 hours, you see that most of the surface is quite still not degraded in terms of unique species, but mechanically it failed after that. Just a matter of fact, if you go also to check on the state of the art, which is the Nafion, which is most used now, we know that there are a lot of let's say species which are because of the oxygen, we create a lot of reactive species. And then the idea is to really produce some kind of stabilizing agents which can be acting as a scavenger from these reactive species. And in that sense, I show you here the recent work of this year we have done, And the idea was really to make some kind of functionalization or double functionalization based on a concept to graft really two different materials and to have really functionality A and B in the same time. And of course, the process is continuous, versatile, and also it was quite straightforward. Just to do some tests or to validate the procedure, we just compare this material with the standard, really other material based on fluorinated material, fluorinated film, and compare it with the state-of-the-art Nafia. And as you can see it here, really the standard and these new materials is quite similar, and also the constructed morphology allowed us to really to see that the similarity between both are quite visible. We did also some durability tests, and as you can see here, for over 1,800 hours, it was quite clear that this material is stable in the fuel cell conditions, of course, single cells. And also the most important part, which we were aiming to, is really the introduction of this barrier of gas, or the reducing the gas crossover. And as you can see it here, we have really lower values and constant values during all the testing time in comparison with standard, really standard state-of-the-art membrane. I think with that, I don't want to go into detail and take much time. I also started to look up a bit on what's going on in Africa. And as I mentioned, I think so far South Africa is the unique and leader, let's say, in the field in the continent. I think we can thank for that the platinum mining sector they have there. Of course, we have also let's say the fuel cell production continues also to increase in Europe and other countries, and I think South Africa is positioning itself because of this let's say the platinum in a critical way in the supply chain, and they are there, and they will be, I think, for the next years. When I looked a bit into a Moroccan context before ending up my presentation, as you can see it here, I think so far I saw only one first demonstrator, or last demonstrator maybe, which was in 2012 in my, let's say, so far I came across, and then it's accommodate really for the stage of unique installed demonstrator, which was really a mix between wind and hydrogen fuel cell system to see the intermittence, see between the excess and generation of electricity. Just the last slide. I wanted to express my thanks to the colleagues from Arizen to inviting me, and of course we are aiming together to really build up fuel cell and hydrogen technology test facilities in Morocco. I think the idea is to really, for us, especially to form qualified professionals and in Morocco with relevant expertise for this new technology. And this is needs really or require human skills and expertise. And this is quite, I think, a good point to go for. Of course, this will help us to accelerate the development of this technology on the next decade in Morocco. Of course, with the help of our partners from Germany and other countries, I think I think this public-private partnership we are starting, and we launched some projects together, PhD projects with Arizen. I think it's only the beginning of a long story of collaboration. And before finishing, I would like also to express my gratitude to some co-authors and colleagues, mentors, Dr. Gunther Scherer, Dr. Lawrence Kubler, Dr. Dirk Hinkensmeyer, and also Dr. Balok also. And thank you for your attention.
Thank you very much for this nice overview and for the state of the art. Also, I believe that Horizon, together with University Mohammed VI and maybe other partner, will make a competence center in Morocco for fuel cell. And also, I'm thinking about also competence center for lithium battery storage and all this stuff in Ben Guerir to really complete this hub of science and technique in Ben Guerir. Thanks to all of you. I will give now the floor to last but not least speaker, so Sipai. I hope he's online. So I will give his biography. Please.
I'm here, yes.
Okay, so you can share your presentation. Meanwhile, I will present you. So you are a chemist and you work in Technical University Dresden on project related to energy conversion. In 2013, you start to work at Fraunhofer Institute for Interfacial Engineering and Biotechnology, IGB, at the Straubing branch. You take part in the acquisition, management, and processing of several public and direct industrial projects related to carbon dioxide, energy, and biomass. I think your talk on potential carbon capture and utilization cooperation with Morocco, OCP, and Horizon is a very important, and we will love to hear from you your conventional methanol with biologic methanol. So the floor is yours, and thank you.
Yeah, thank you very much for the kind introduction, and I would also like to thank to the organizers for giving me this opportunity to present our competences in CO2 conversion to fuels and chemicals. Now I had to switch off my camera because the bandwidth is pretty low, and it is either sound or voice and nothing.
Okay.
So that's why I'm sorry that you cannot see me on the camera. Hopefully the bandwidth is still okay until the end. If not, then I will have to restart it again. Do you see my screen?
Yes, we see.
Okay, fine.
Leonard, if you could just remove the right band from your PDF. If you click on the arrow, I don't know if you can see it, in the middle of the screen. No, horizontal arrow. Sorry, it's on your left. Again, in the left. Sorry.
Oh yeah, this one.
Thank you very much. Thank you.
Thanks a lot. Yeah, so it's always good to be towards the end of a conference because all the previous speakers have concepts like technologiness level and hydrogen and the necessity for doing all these kind of things. So that gives me a quite good introduction, and I can build on these concepts and to get directly to the point of my presentation. So here I just summarize up what is actually how does the knowledge go from academic research to industrial production. This is a very long way, and unfortunately, as you can see on this figure, the investment is also not evenly distributed between the different levels. and there's a quite significant gap in between, and Fraunhofer is as such as Fraunhofer society as a whole developed processes to fill the gap between academia and industry. There's also another minimum curve, which is shown up here in this part. And this is actually also a cash flow curve, which shows that in the beginning you need to invest quite a significant amount of money, and once the system runs and it starts to produce the products and the products are commercialized, and then this goes upwards. And depending on the scale, of course, the thickness of these curves can be different. For some of them, it might be that the zero is never crossed, and this is, of course, not optimal. The objective is always to cross somewhere the zero, so that the system starts to produce to pay back the investment and to produce profit. We have to consider these developments also, of course, from the dimensions of the sustainable development, which is on one hand aspects of economy. Ecology is that we know very well, and we have heard about it in the last days, and also the social aspects of the development. So we are focusing our attention among all these three aspects. So now going to Fraunhofer IGB, we are a relatively large institute spread across Germany. The headquarters is located in Stuttgart. There is a site in Leuna, and our branch IGB Biocat is located in Straubing. This is the youngest branch. We started a little bit more than 10 years ago as a greenfield project, so to say, because as you can see here at the corner of the building, it has been really erected from a greenfield, and since then we have established ourselves as an institute which focuses on the work on the research and development for processes to convert carbon dioxide and biomass into energy carriers and chemicals. Although this is something that many other research centers do, our philosophy was to bring under one roof competences from chemistry and biology, and to combine chemical and biotechnological processes in order to enhance the efficiency of these processes. The methanol synthesis is, of course, a very prominent pathway towards achieving these goals, because methanol is a compound that can be transported very easily, and it can be blended also easily into fuels. But we also convert further the methanol into fuels, which are drop-in fuels, which have a much higher energy density compared to methanol, and it can be used directly in systems and in transportation equipments which cannot handle methanol. This is, for example, the aviation. Their methanol, for example, is completely not possible to implement. They need liquid fuels, hydrocarbons, which are compatible with their own systems. On the other, methanol can be converted also relatively easily by biotechnological processes into compounds which are chemically not really possible to be prepared, and we address also these processes in our projects. Now to quick start into our competences in methanol synthesis. We started, of course, on the catalyst level. We produced some materials, and as you can see here, our third catalyst has approached already in 90% the state-of-the-art industrial catalyst, which has been developed over 50, 60 years. So that shows how steep is our learning curve, and how fast can we go on with these kind of developments. Of course, in the meantime, we have reached also other milestones. For example, we have made possible to turn this catalyst synthesis from batch operation mode into continuous mode, which means quite a significant saving in time and also OPEX, because the reactor produces much more catalyst in the same amount of time, and that means also that the energy demand for this synthesis per kilogram material can be reduced very, very significantly. Then we have set up our lab in order to enable the chemical conversion of hydrogen, CO2, and even syngas mixtures towards methanol. These systems enable also to perform water gas shift, steam reforming, so to look at the intermediate steps of methanol synthesis, but also to look at the downstream processing of methanol to olefin, conversion of olefin to diesel, and to convert methanol into diesel gasoline in one cascade reaction that is being enabled by this extendable reactor units that we have here. We also got a quite large reactor system that enables all these reactions also in parallelized manner. That means we can speed up the data acquisition in this system, in which we have 4 parallel channels. We have also an online GC-MS analytics, and that speeds up very much the data acquisition. This system is also enables us to do research and development on the catalyst level for ammonia synthesis as well. We've got also a parallel screening unit for batch operation. This is a conventional autoclave system that enables also methanol synthesis and related reactions too. Then we built up the equipments for biocatalytic further conversion of methanol from small few 10 milliliter scale up to 40 liter. And at our colleagues in CBP Leuna, they have also a cascade which starts from 10 liter and it goes up to 10 cubic meter. So we can cover a very, very large interval of scales which is needed for piloting these these processes. And then when we were almost ready with all these preparatory work to set up equipments and competences, the colleagues from Dechema, they have finished their economic estimations on the methanol synthesis unit, synthesis process, and they came up with this little table that shows the cost estimates on renewable methanol synthesis in function of the electricity price and also in function of the operation time over the year. And when we put that price matrix in comparison with the market price of petrochemical methanol, then we see that we have here three areas. The economically viable area is only in this corner with very low electricity price of 10 euros per megawatt hour and pretty long operation time, over 5,000 hours per year. Then we have marginally viable areas that is around here. If we would have high crude oil price, and that is and the intermediate sector that would cover already 3,000 hour operation. And then we also have quite large areas in this price matrix, which are at the current prices not viable, and that is because of high electricity price, and also we would need to have long operational times. In the same work, they also identified what are the vectors for economic viability. Of course, we would need to have access to cheap electricity, concentrated CO2 source, and high load factors over the year that we have seen it here, and long operation time over the year. And this is in most of the geographies in Europe unfortunately not possible, and that's why we looked at what could we do to make this still profitable business also in European landscape. And that's why we developed this combined chemical biotechnological process, which is basically relatively simple combination of conventional methanol synthesis from CO2 and hydrogen with the fermentative further conversion of methanol. And I would not go now into details, but this is how it looks like. The methanol synthesis takes part in this box here, and then after condensing the methanol, we simply feed it into the fermenter, and you can see that after a while the microorganisms which are in this fermenter, they start to convert it, and they formed CO2 based terpene.
You have 2 minutes.
Yeah. Something happened here, just a second. The product spectrum is pretty large. We can tune the microorganisms to produce all these organic compounds, which are used in the industry for various purposes. and most importantly, their market price is well over the methanol market price, and that makes the business case suitable also for small scale and remote operation of CO2 conversion. As you can see, we have a much larger market price, and that enables us to have positive net present value for such kind of combined processes. Here we have summarized up the technical advantages of this process. Most of them I have already mentioned. Most importantly, that we don't have to separate methanol from water. The second step, the fermentation runs at 30 degrees, and this makes it all very interesting from a technological point of view. Now, half a minute for our project that was running in parallel here. We have this idea that we set up to convert hydrogen and CO2 into methanol, feed it into a direct methanol fuel cell, then that releases the energy into various applications. It releases also the CO2, and then we, with the use of renewable electricity, we get the hydrogen, and we make this circular process. On the other hand, we have also a big EU project that is now in the final phase. Here, our idea was to convert electrochemically the CO2 into ethylene on the cathode side, and on the anode side to get hydrogen peroxide from water, merge these two things into ethylene epoxide, and then finally to convert the epoxide into ethylene glycol. As you can see, the market for all these organic compounds is pretty large, and it is growing. So there's a real big market for all these products. Finally, I would like to conclude my talk by referencing the cooperation with Morocco, which was already introduced in the previous talks. This is the Green Ammonia project, which was started about 2 years ago. In early 2019, we have presented our study on green ammonia production, and since then the cooperation goes on further, and we are very happy to be able to cooperate with the Moroccan stakeholders, and we hope for the good continuation and extension of all these cooperation. And with that, I would like to thank you for your attention, and I'm happy to answer your questions.
Thank you very much. Thank you very much for this very interesting talk on methanol business. I think your competitive results are very good, and also your electrochemical CO2 reduction, the new project to find ethylene glycol is also very important, and also the fact that you have already cooperation with Erizen and University Mohammed VI is amazing. And this kind of project, this kind of research and prototype is not only for Morocco, but also for the whole Africa, will be interesting. So I will open the floor for all of us. I want to start with Thomas Hannibal because he has to leave, I think, in a few minutes, just to give his overview about all these research, since he has also an a vision on regarding the program in Germany, portfolio in Germany on fuel cell, on his own research on ethanol. Maybe he can give us some highlight. And we have some general questions like the key result of scientific research in Power-to-X as well. So the floor is yours if you can tell us something, Professor Hannibal.
Yeah, as I already was mentioning in my presentation, there is the whole area of photoelectrochemistry. And the question which arises and which needs to be discussed, I think, is how to bring this into the application. How far is it away? I think we are in a range, what we are discussing here, where we are dealing with technologies which need to be developed and which are at different states of the TRL, of the technology readiness level. And I think it's like maybe comparable to how to deal with the corona pandemic, since we need to do things which are right now developed, but we are under urgent pressure, and there is some high potential for applying it, but we need to estimate and to see when and what do we apply where. And I think this is the one part of the discussion. What are the drivers for different technologies? So we have maybe high risk but high reward lines, courses to follow. Then we have more established technologies, maybe, for example, for producing hydrogen. Nowadays, the combination of a electric power generator like solar cells or wind or anything else, plus an electrolyzer, has a higher TRL. But of course, on the other hand, there would be maybe more potential for other technologies like the artificial photosynthesis. So I think this is one question to discuss, and how to do this in the best way. And my opinion at this point is that the key driver, and we have seen this in the past, is not only to deal with cheap materials. So to be cheap, this is something which needs development. We have seen this in the PV. I think this is a very good example where we have seen that costs came down by more than 2 orders of magnitude. And not the cheapest material only made it, rather the very efficient materials and the very efficient technologies finally are appearing to make it. For example, not only the thin film technology was successful, rather the crystalline material, the crystalline silicon, for example. And sometimes one has to drive the market also, and it follows different rules and ways how maybe scientists would evaluate or estimate it. So the question is, where is the research now and where is the industry now? And how could we do this split in the best way? It's very clear from my point of view that many elements of research which are very important and very good for the photoelectrochemical way, for the artificial leaves, would be also very good for applications in other ranges. Just to underline this. For example, catalyst development. This is very important for, on the one hand, the dark electrolysis and also for photoelectrochemistry. Or optoelectronics tandems are very good for photovoltaics, in particular also concentrator photovoltaics. And all who are developing photovoltaics right now are desperately trying to find good tandems for future developments. Or for example, the solid-liquid interface is very important also for batteries. So there's many generic elements of research which are real breakthrough technologies. So just to bring this into the discussion, how to decide which technologies should we choose, where should we go, and in particular, if we are dealing with technologies which we are under high pressure of development.
Thank you.
We think in our approach, we are following several technologies. One basic technology, the artificial leaf, but surrounded by several technologies which are really worth to follow in a larger, complex interaction of teams, countries, research, everything.
Your proof of concept with the 3,5 compound, which lead to 19% efficiency with for hydrogen. Do you have now any requests from the industry that they want to develop your system, or this stay thinking that is fundamental and so on?
Yes, like we have seen this also in the former presentations. For example, in the last one, there is always some difficult situation for any kind of development after the feasibility study made by the proof of concept, then the development further, and then trying to bring this into the market. If you define different phases of development, then this might be the third phase. Before it's really going into the market, you need to do a demonstrator. And that's what we are right now starting to do. Very fresh, very new. So right now we have a large project surrounded by industrial partners, and they really want to follow this way. That's what I'm saying. It's surrounded by different important technologies. The growth of the devices, there is new development necessary if you want to do this on a large scale, on large areas. It's normally epitaxy is something where you have load in, load out technologies, high processing costs. This must need to get into an inline process. Secondly, the whole architecture of the device, how to bring this into the harsh environment, of course. So the module development, the machinery development, then the catalyst improvement make this less precious and costly. And yes, there is quite much industry. There's several partners in this project, and even several partners more, which are very interested, either in the gas handling, or in the catalyst development, or in the machinery development, or in the, like Arthur Space, for example, a growing company dealing with multi-junction solar cells for space, but also terrestrially, and this would also be something which would be great. This is very exciting technology for the future, for the whole market of electronic, optoelectronic, and so on.
Okay, thank you very much. I don't know if Sipai heard us, because we don't see him. Sipai?
Yeah, and I want to thank
Yes.
you again, just to say this last but not least, thank you so much, and I'm very impressed always, and I'm very glad to be able to contribute, and just saying thank you, and sorry that I leave,
Yeah,
otherwise
it's okay.
I won't catch my train. Yeah.
Don't forget, we will also discuss a little bit this workshop after some time, yeah?
Yes.
Okay.
Yeah.
Okay. Thank you so
very
much.
Professor.
Thank you. Thank you. Thank you.
Thank you.
Yeah. Okay. So Sipai, he don't answer. He could be maybe.
Yeah, I'm here.
Ah, very good, very good. So I want you to, because your talk is just fresh, the last one, and I want you to, if you can tell us a little bit about, are you now going to the industry with this methanol, with this business plan what you have now, and also about electrochemical CO2 reduction to ethylene glycol? That's one thing. And is the project what you have in common with Morocco, or is something else?
Yeah, we have here several projects running in parallel. Particularly this electrochemical reduction of CO2 to ethylene is an EU project. It runs with several partners from across whole Europe. And of course, each partner has its own part in it. Some of them are working on the electrochemical reduction of CO2. Others are working on the electrochemical hydrogen peroxide synthesis. Also, others are working in the design of electrochemical cell on larger scale, because this is also not that trivial. Other partners are dealing with the membrane design, and we are here at IGB responsible for the conversion of ethylene to epoxide and ethylene glycol. So this is to briefly outline how does such an EU project look like. Okay. For other projects, some of them are publicly funded, the others are direct cooperations, like the one with Morocco for the green ammonia synthesis. And to address the question about how to bring this into industrial operation or closer to industrial operation, there are, of course, several steps. In our labs, we are, as I have shown, we are moving between TRL 3 and 5, and that is still relatively far away from what the industry can apply. And we have to look first for industrial partners who are interested in deploying such kind of a technology. This is the very first step, and then to come to a discussion and define how to go on further. And there are several opportunities, either to do a direct cooperation with the industry, or to look for public funding, like, for example, an EU project. If we choose direct cooperation, this is certainly the fastest one and the most secure, because then we do not depend on a long procedure that we need to write a project application and wait until it goes through, and if it goes through or not, because that is also a very important factor. So if we think about direct cooperation, then it is pretty simple, because then we just have to make a cooperation agreement, and from there on it goes pretty straightforward. making a plan how to tackle the issues that we have in the way of upscaling, and even to bring in new partners, for example, electrolyzer manufacturers or reactor manufacturers and so on. And that's how such a bigger consortium is established. And then when this is established, then the pilot or demonstrator build-up can start. So this is the usual pathway of how to do it. And about the publicly funded project, it is so that we have to find the partners, most likely from all across Europe, and we have to find the good balance between academic partners, applied research institute partners, and industrial partners. And then it kicks off with a writing of a proposal, which has to be, of course, a very excellent proposal in order to have some chances. And then it is submitted, and after about half a year, we have the decision from the EU Commission.
Okay, thank you very much. Thank you.
Yeah.
Now, I would like to ask our Moroccan partners, Professor Denoun,
Yes.
Dr. Samir, Professor Hisham, and Leon, also you can stay with us and give us your experience. There is one question which consists of capitalizing on the result of scientific research and developing also niche for scientific research in our country, in Morocco, and in developing country in general. Can everyone give his thought about this? Because this concerns us very much. So who want to start? Yes.
I can speak?
Yes, sure.
Yes. In Morocco, in this technology, hydrogen technology, we have many opportunity for younger. For example, hydrogen installation of storage hydrogen in outer road is very
highway, yes.
It's a very good opportunity for desalination because renewable energy is very intermittent. With hydrogen, with fuel cell, with hydrogen, it is possible to reduce opportunity when agriculture can be pumping, irrigate in the night, because in the night not have evaporation. Donc, it's very interesting for agriculture. For industrial, for example, have three groups in 124. If the industrial like to have system multi-source renewable energy, problem is intermittency. If we introduce fuel cell, the industrial can be working for three groups in this 24. That is very interesting for industrial. And also Morocco imports 2 million tons of ammonia. Is the big factor for money for UCP and Morocco. It is necessary to develop engineer in synthesis of ammonia, reduce importation for Morocco. That also is the good opportunity for university and industrial. Thank you very much.
Thank you very much. This is very important point. Ammonia, and I think is one of the milestone of Irizen, I guess, is the development of ammoniac using hydrogen, green hydrogen and nitrogen. The way how to do this, of course, has to be discussed in the industry.
I discussed with Badr Ikan in one project, one deposit, one project with the University and UMC's pay and the Foundation also pay. In this project, we can develop unite mobile unite with multi-sources with fuel cell in order to develop water. You know, Morocco now live very good problem of water. It's possible to develop water in one basin hydric. Bhera is between Al-Masira and Gentour. Donc, it is possible to develop many installations in order to produce water. Et the water is c'est de l'or, c'est complexe. Pour l'instant, donc voilà, les gens ils vivent une situation vraiment catastrophique dans les régions du Maroc et en particulier Hamna. Donc, it is possible to.
Okay. Water is very important, and we have to take it as a priority. Thank you very much. I will give now the floor to Samir and Hisham together to discuss with us. Irizen and University Muhammad says they have a lot of resources, and they have also a lot of willing to do things. And if I saw what CEO Badr Ikan has done from 2011 until now, it's a huge. And I want to know how you can boost this business, power to X in Morocco. And there are different things we have seen today. Can you tell us a little bit, Samir, you have already shown a lot of things, and we have also seen from Hisham the fuel cell, and obviously he's expert in this, and we can count on him. So can you tell us a little bit, how do you see the future of research and development until to go to scale up and the industry? How can you?
Yeah, thank you very much for this kind question, Professor Nawi. And the challenge is to make it in 2 or 3 minutes, because I've been told by the organizing committee that we are 30 minutes ahead beyond schedule. But yeah, of course, I think to be really short and concise, we have seen many promising things. And as you said, Irizen, together with its partners and also Moroccan universities, has helped also create some momentum in the university in terms of renewable energy and technologies and this application. And now the challenge is to go a little bit further with this new revolution in terms of hydrogen, green and green molecules. And I think, as you said, Professor Nawi and all the colleagues, we have the necessary ingredients. And also the vision now, also with our ministry, things are really clear among the commission, National Commission on Power on Green Hydrogen. So I think we have all the ingredients. Industry is ready, government is ready, and also research and universities are ready. So as the French says, I think y a plus qu'à. I think everything is ready to do very outstanding things. And I would like to conclude with this. Thank you very much, Professor Nawi, for your challenge.
In my case also, I think we have really a great opportunity in Morocco really to go ahead. I think, as usual, 2 things has to be said as quick as possible. The policy, it has to be stated to really build on it. And with that, I think we can go further in research and development on local, let's say, valorization of what we have in materials, in terms also of technology. And also we can count on our partners also to not redo the wheel. We have already things which are already built. We have really to build on them. And we have, let's say, the infrastructure. We are building our infrastructure. That means we can go for new things. I think we are more flexible than other countries in Europe. because we are building the country and we are developing. That means we can go from now on a new, let's say, technology, and then go ahead in that sense. And then I think we have to form the next people for that.
Thank you very much.
Ahmed,
I think we have to close because now
Ahmed, one question.
Yes.
Yes, I want address of Ben Youssef. It is possible to have your address. It is.
We will do it. We will do it behind the scene. We will do it.
Yes. I don't. Address.
We will do it. Thank you very much. With that, I would like to thank the organizers, Arizon University Mohammed Sis, and especially from my side, Badr Iken. I know him. He did a lot, and we see these 3 days. I want to thank the organizer again and all people behind the scene. I know that they have worked very hard the whole time. And the last word is God bless Morocco. So I give the floor to the organizers.
Thank you, Professor Ahmed Nawi, and all the speakers and the participants for this very fruitful session. Before ending this very insightful World Power 2X Summit, let me give the floor to our host, Mr. Badr Iken, for a rewind of these last tremendous 3 days of discussions and interactions. Mr. Iken, the floor is yours.
Thank you very much, Selma. Ladies and gentlemen, dear friends and colleagues, on behalf of the organizer committee of the World Power 2X Summit, I am delighted to have hosted you during this amazing summit, which covered a promising topic with many passionate and inspiring speakers. We were able to attract more than 5,000 participants from 60 countries, and we had the participation of decision makers, regulators, industries, technology and service providers, project developers, as well as researchers and students. Today, we must unfortunately leave, but we are glad for having set up a crossroad for you, a crossroad for all the green hydrogen community, for sharing our visions, strategies, first experiences, and challenges to make our world cleaner through a new era of green hydrogen economy. We don't have the time to repeat all the important messages and statements from our 12 sessions, but allow me please to take only 3 key messages. The first one, green hydrogen will clearly help to decarbonize the European and the African economies, and it represents a real social economic opportunity to have a better distribution of wealth and the more prosperity through the development of the energy sectors as well as transformation industries and all the other important infrastructures. Secondly, we need more international and regional cooperation. We have to develop new kind of energy partnerships, and it must be oriented to the most essential factor of resilience, human capital, through more investment in training, capacity building, R&D, and innovation, and pilot projects. Thirdly, thanks to the vision and leadership of His Majesty the King, Morocco is ready to face the challenge. I have also to take the opportunity to thank, namely, all our supporters and partners, starting by our Minister, His Excellency Mr. Aziz Rabbah, as well as all the ministers, state secretaries, and distinguished chairmen, panelists from Morocco and from all over the world, with special thanks to Germany and our German partners. I would also like to thank the Ministry of Energy, Mines and Environment, the Mohammed VI Polytechnic University, OCP, and all the other strategic partners, beginning by CGEM, the Moroccan Confederation for Enterprises, the Moroccan Energy Federation, as well as IRENA, DII, Konrad Adenauer Stiftung for the important support, the German Chamber of Industry and Trade in Morocco, and the German-Moroccan Energy Partnership coordinated by GIZ. Of course, I have also to thank our sponsors, ENGIE, John Cockrell, Enel Green Power, GIZ, the Regional Center for Investment, Gelmim Wednoun, the H2U, the Hydrogen Utility, CWP, EDF, and our media partners, les Inspirations Eco, EcoActu, Le Vert, Énergie Environnement, und der Afrika Verein. I have also to pay tribute to all my colleagues, with a special thanks to Dr. Samir Rashidi and his team, Mr. Ayoub Hertz, Mrs. Nuhaila Nabil, Mr. Usama Baisi, Mrs. Ilham Uria, for the amazing organization. I have also to pay tribute to Mr. Muhsin Ben Mizian and Umayma Al-Faris for the perfect event management, to Mrs. Selma Tezi and her team, Mrs. Jihan Hussein, Mr. Rashid Taiq, and all the other colleagues behind the scene, from IRISEN, Mrs. Duri, Mrs. Fikri, among other colleagues from IRISEN and Green Energy Park, who clearly contributed to the success of our event, the success of these events. Last but not least, I have to thank Faisal Tedlawi and his stage team, Hatim Ben Jelloun from the consulting firm PAS and his team, and our guest moderators, Ayman Sharqawi from the Mohammed VI Foundation for Environmental Protection, Professor Ralph Verspon from the Fraunhofer Society, and my colleague Selma Tezi from IRISEN. To finish my intervention, I would like to officially invite you to the next World Power to X Summit to Marrakesh, the 1st to the 3rd of December 2021. We all would be glad to welcome you in our wonderful country, to share knowledge and to continue shaping the future of our world, of our cleaner world. Wishing you all the best. Stay safe and see you next year. Bye-bye.